Okay, ignore the section number because we're probably going to use a packet, although I think this is from your current textbook, section 5.4, but we're going to do the topic of optimization. And I'm going to do this with a couple of examples. If we were in class, I would show you a poster board. But I had a poster board that was 28 inches by 22 inches. And my task, I want to make an open box by cutting 4 squares out of the corners with side length X inches. And I want to maximize the volume of the box. What do I do? So imagine if where I have the dashed lines, I'm cutting that and then folding up the ends. So I get a box that looks something like this. It's just a box with no lid. Clearly this would not be folded, so I'd have to, tape it up or somehow. So I want to maximize the volume of the box. So the first thing I need to do is think about my dimensions of my box if I fold this up. So this is 22 inches across here, and it is 28 inches here. Whoops, went a little too far there. But I need to think about the length of the box that I'm going to have. This is my poster board. But if I'm cutting it here and cutting it here, then I'm cutting off X amount. So the length of the box would be 28 minus 2X inches. And the width of the box would be 22 minus 2x inches. So make sure you realize that. And then the height of the box is going to be x, because that's the amount that it is folded up. Well, what am I going to need to know? I'm going to need to know the volume of the box because I'm trying to maximize the volume. So I need an expression for the volume. Well, we know volume is length times width times height. So that means it's going to be 28 minus 2x times 22 minus 2x times x would be my volume of the box. So I'm going to do a little bit of factoring, to kind of simplify this. So notice I can factor a 2 and I'd have 14 minus x, and I'm going to factor a 2 out of my width and have 11 minus x. This is still going to be an x. So I'm going to do 2 times 2 is 4x times 14 minus x times 11 minus x. And here I have the volume. So it's going to be a little convenient if we go ahead and multiply this out to come up with a polynomial expression. So I just already did it. And I would put this in a box. I know you guys could do that. So when you finish this, you get v equals, for the volume, 4x cubed minus 100x squared plus 616x. So you could either trust me on that or work it out, but I know that you know how to multiply that. So I am trying to maximize this expression. So think about, how do I find the maximum value of a function? Because that's what I need to do. I want to find the maximum value of a function. Well, hopefully you remember that we take the derivative and we set it equal to 0, and we look for if there's, if it's positive or negative, and whether when we find a maximum. So I'm going to have to start by finding the derivative of the volume. So when I do that, I get 12x squared minus 200x plus 616. So what's the next step? You find the derivative. We did this before with f of x and f prime of x. Now we're just doing this with an applied situation, but it's still the same process. Find the derivative, set it equal to 0. So we're going to set to 0. And then we're going to find critical points, which we've done before, just not in a setting like this. So when you do this, we're going to use our calculator. So I put the function in my calculator, and then if you go zoom 6 with a standard viewing window, remember what we're looking for. We're looking for the zeros. I need to write down set it equal to 0. And I see one of them. Now I know that this is a parabola and it opens up, so I'm seeing the first one but not the second. So then I'm going to just adjust my window in the X direction. X max I want to make larger. I'm going to make it 15. So you can just kind of adjust that as needed. And now I can see both of those. So if I do second calc 0, and I'm going to do 3 as a left bound because I have this counting by ones. And I'll do 6 as a right bound and 4 as my guess. And then you see I get, for one of my solutions, X is about 4.078 if I go correct to 3 decimal places. I'm just going to leave it to you to check the other second calc 0 over on this side, and we would get 12.589. So again, I'm going to make a comment here about setting this equal to 0, since that's what we're doing. Now, remember the next step would be to make a number line. So this is V prime. So I'm going to mark my critical points on here. And then I'm going to use the graph I'm already looking at. If this was a calculator problem, this would kind of suffice as my work, but remember, not my explanation. So I can see that to the left is positive and to the right is negative because it falls below, the parabola does. So this is positive, this is negative. And then to the right of the 12.589, it would be positive again. So I am looking for the maximum volume. So I'm looking for where the volume changes from positive to negative. So so for my solution, I have a maximum volume when X is about 4.078 inches. And then if I needed to know what that volume is, I can plug back into my expression for the length. Remember, my length was 28 minus 2x, so you can just do the math there. Hopefully I have these correct. I have 19.845 inches. The width, plugging that back into my expression for the width, I got 13.845 inches. I have not really double checked those. And the height, of course, is just the value of X, so 4.078 inches. And my question was to find the maximum, I wanted to know what is the maximum volume of the box. So if I multiply length times width times height, I get 1,120.310 inches cubed. So that would be my maximum volume of the box. For this next example, I have a pop can. Here's a picture of one. And my pop can, this is a standard pop can, is 12.3 centimeters tall and 6.5 centimeters in diameter. Now, I mean, it's not perfect because it has the little, indentations there, but close. So the question, can you design a better can that holds the same amount but uses less material? So, that would be important if you were a business making pop cans. Then if you use less material, then theoretically that would cost less money to produce that can. So let's see if we can come up with something that would still hold the same amount. So you have to kind of think about what that means. The volume, I told you right here, the volume is the same, but we're going to minimize the surface area. So that means you're going to have to know the volume formula and the surface area formula. So we can find the volume of the existing can. So if we take pi r squared h, then we, because that's the volume of a cylinder, would be pi r squared is the area of the base times the height of the can. So we would need the radius, and then we have the height here. So that's how you find the volume. So we would have pi r squared. If the diameter was 6.5, then the radius is 3.25, and times the height, which is 12.3. So I get approximately 403 centimeters cubed. And that would be the volume of the existing can. So the two formulas I'm going to be making use of is volume equals pi r squared h, and I need the surface area formula. So if this was something on the AP exam, they would say something like, recall that a surface area of a cylinder, and they would give you that formula. So we have the surface area is, well, you've got a bottom and a top circle. So 2 pi r squared, because pi r squared would be the top, pi r squared would be the bottom, so you have two of those, plus 2 pi r h. If you were to cut this can, get rid of the top and bottom and cut the can and then unfold it, you would have a rectangle, and the base of the length of the rectangle would be 2 pi r, because that would be the circumference of the circle, and the height of the rectangle would be h. So that's kind of where you can, think through that formula, but it would be given to you. So the volume is not going to change. So I'm actually going to do a little work here and plug in. I'm going to actually solve. I'll plug in a 408 for the volume. And I'm going to make a substitution here. I'm going to solve for h. So when I solve for the height, I get the height is 408 over pi r squared. So what that's going to allow me to do is I'm going to take this and plug it in up here. In place of the h, I'm going to put this expression. I had too many variables. So if we did this once before when we were doing related rates, and we wanted to simplify this, because I'm trying to minimize the surface area, which means I'm going to take the derivative of this formula, but I really don't want two variables in that case. So I am replacing the h with 408 over pi r squared. So we end up with 2 pi r squared plus 2 pi r, and replace the h with 408 over pi r squared. So then we're going to just change the formatting of this a little bit. I'm going to leave this 2 pi r squared. And when you simplify this, the pi's are going to cancel. This one of the r's is going to cancel. So you're left with 2 times 408 is 816 over r. So I'm going to change this one more time to 2 pi r squared plus 816 times r to the minus 1. So that I can set it up to find the derivative, because that's what's next. So a prime, we're going to take, with the power rule here, I get 4 pi r, and because we're taking the derivative with respect to r, and then over here I'm going to have minus 816 r to the minus 2. So now I've got 4 pi r minus 816 over r squared. Need to find a common denominator, so I'm going to multiply top and bottom by r squared. So now I've got 4 pi r cubed minus 816 all over r squared. So this is a prime. I am trying to minimize the surface area. I want to minimize that. So I'm going to have to find the zeros. So I'm going to set this equal to 0. Now I have a rational function that I want to set equal to 0. So that means I can just set the numerator equal to 0. So 4 pi r cubed minus 816 equals 0. I can add 816 to both sides. Divide by 4 pi. And take the cube root. So I get r is approximately, okay, so over here I did that, and I get about 4.019, and I believe I am in centimeters. So I need to verify that that is, we're looking to minimize. So this is my 0. I'm going to take something smaller than that and plug it into to my derivative for that. I'm just going to tell you if you do that, like you can plug in a, well, I can't plug in a 0. I have to plug in something because it has to, I have to be able to plug that in for r. So you can show this. I'm just going to tell you that you will get a negative if you plug in something less than 4.019, and you get a positive if you plug in something larger than that. So you could look at on your graph, or you can just plug in a value less than or greater than that 4.019. So then when we look at this, because the derivative is changing from negative to positive, that means my function's going from decreasing to increasing, which means this is a minimum. So I could say, since, and I should have done this on the other one too, since a prime changes from negative to positive, the surface area is minimized when r equals 4.019 centimeters. We can plug this in to find the height because we had a formula for the height. If you look back, remember we said the height was 408 over pi r squared. So that would mean, and the height is, if you plug that in, you will get 8.039 centimeters. The minimized surface area is 304.524 centimeters. I just centimeters squared. I just plugged in the values for my radius and height into our formula for the surface area. So we could do that. If you compare this compared to 317.443 centimeters squared of current can. So like if you took the dimensions of the current can and you plugged it into the surface area formula, then you would get this. So you might look at that and say, well, how significant of a difference is that? Why don't they do that if it's going to be less material to use? There's other things. If we were in class, we'd kind of talk about some of those things. So some of the other things, a reason why they might not change that is if you think about the average size of a person's hand and holding a can, that can be an issue where if it's 2, this would be, we would be changing remember our radius was 3.25. So we would be changing that to 4.019, which means the diameter would be over 8 centimeters. So there comes a point where it might not be comfortable to hold the can. If they changed this, think about some other implications that would have would be the cup holders in your in your cars possibly could be changed, would have to be changed. So it might not be worth it to do that. So anyway, but this is the idea behind it. This is called optimization. You're going to have some problems where you have to make use of this.